This video lecture is the last in our series on thermochemistry, and it will cover entropy and Gibbs free energy. So in your thermodynamics packet notes, if you will turn to the very last page of your notes, right underneath bond energies, it starts a discussion of something called entropy. And if you'll look at that very first paragraph, it talks about chemical reactions as far as the enthalpy goes, heat goes. Nature favors exothermic heat-releasing reactions. And those reactions, remember, have a change in heat value that's negative. Well, we know, though, that there are some endothermic reactions that still happen spontaneously. Nature does favor them. So there must be something else besides the heat part, the change in heat or enthalpy, that governs whether a reaction is going to take place. And there is another force at work called entropy. Entropy is a measure of chaos or disorder. Unfortunately, the letter that represents entropy is kind of weird. It's an S. I don't know if it comes from chaos or disorder, but anyway, it is delta S for change in entropy. And remember, that's a measure of chaos or disorder in a system. What I want you to do is look in your notes, and there's a section where it has this part listed for you, and I want you to highlight that or put a star by it. That's important. The delta S value being positive is what nature favors. That means something is becoming more chaotic or more disordered. A negative value for entropy is less disorder. That is not favored by nature. Just as a side note, I know at the very beginning of the notes we talked about the first law of thermodynamics being the one about the law of conservation of energy. The second law talked about that nature tends towards a greater state of disorder, which is talking about entropy. And then finally, the third law also deals with entropy. It says that the entropy of a perfect crystal at absolute zero is exactly equal to zero. That's because at absolute zero, there's no movement, so there's no chaos or disorder. How that will tie into what you're going to see in our calculations is you'll see that unit of Kelvin come back into play in the units of entropy. You will see the Kelvin unit as part of the entropy units. And that is based on this idea that we need a reference point for a beginning where there's no chaos, and that would be at absolute zero. All right. Here's some simple guidelines that will help you decide whether or not a reaction or a scenario or a process is increasing or decreasing in entropy. First of all, as you move from a solid to a liquid to a gas, you're going to get more chaotic. That's because the particles are moving faster and faster and faster and faster. Number 2 says dissolving a pure solid or liquid in a solvent increases the entropy. When you take something that's in a solid, crystal, organized structure and dissolve it, it breaks apart. Whether it ionizes and you have all these ion particles floating around, or even if it doesn't ionize, it's still particles broken apart and floating around. That's way more chaotic than the solid crystal structure. Number 3, we don't use a lot. It just says the more complex the molecule, the greater the entropy. What it's based on is electrons. The more complex a molecule is, the more electrons it has zooming around. So that's a greater degree of chaos or entropy. And then finally, number 4 says that increasing the number of moles of particles from reactants to products usually increases the entropy. So I'll draw an example of what that means by that example 4. If we took water and it broke apart into what it's made of, which is hydrogen and oxygen, and we balance the equation. Okay, you can see that on the reactant side, I have 2 moles of stuff, and on the product side, I have 3 moles of stuff. I'm increasing the number of moles, so I'm increasing the particles that are out there, and that increases the degree of entropy or the chaos. All right, so I want you to try example number 6 in your notes. These should be right underneath those guidelines. And all you're going to do is do an up arrow or a down arrow, indicating whether the entropy in each one of these situations is increasing or decreasing. So you can pause the video at this point just to give yourself a chance to try it, and then you can restart the video to check your work. Okay, so we're back. Melting ice at room temperature. When you melt ice, it is going from a solid to a liquid, so that is increasing in entropy. Condensation is from a gas back to a liquid. The particles are slowing down. They're getting more organized, so that's a decrease. An iron nail rusting outside. Sometimes it's easier to look at that reaction happening. When an iron nail rusts, it combines with oxygen, and it makes a compound. When I go balance that equation, I can see that on this side of the reaction, I had 7 moles, and now I only have 2. I'm getting more organized, so that is a decrease in entropy. The same applies for number 4. I went from having 4 moles to only having 2, so that's also decreasing in entropy. And then finally, this last reaction, I have 2 moles, and over here I have 3 moles of stuff. I also am going from a solid and a liquid, which is way more organized and closer together particles than aqueous, liquid, and a gas. So I am increasing in entropy for that reaction. Okay, so just using some simple guidelines, it usually makes a lot of sense in your brain to apply those guidelines to situations. There is only one calculation with just entropy, and it looks a lot like one that we did already with enthalpy. It is using a table of standard values. What's going to be different on the table is their entropy values. So the units are going to look a little bit different. You're going to see the symbol delta S, which represents entropy. And you will also see elements. Elements will appear on an entropy table because even though elements don't have a heat of formation, we didn't see them on our enthalpy tables, they do have a degree of chaos because they have electrons. So elements will be located on these entropy tables, and we just include them in our calculation. So it is the same format when we use this table. It's still the total change in entropy of the reactions equal to the sum of the products' entropy values minus the sum of the reactants' entropy values. So let's try number 7. All right, so there's our table and our reaction. And again, we're going to be using the change in entropy of the reaction is equal to the sum of the products' entropy values minus the sum of the entropy values for the reactor. All right, well, it gives me this value right here. So I can go ahead and put that into my problem, plus 605.9. And then I'm going to add up all my products. So I have 1 nitrogen, which is not on the table, so I'm going to put X. Plus I have 4 waters, so 4 times 188.7 minus my reactants. So I have N2H4, one of those, 121.2, plus 2 hydrogen peroxide. 2 times 109.6. Okay, I'm going to let you pause the video at this point, do this calculation, and see if you come up with the correct answer. All right, you should have come up with 191.5 as your value. And then if you're not sure about what to do with the units, always look at your table. It gives you the units in the table. And they're a little bit weird for entropy because there's a lot of things included in its measurement. There's some energy, there's joules, and it has moles of whatever the amount of stuff is that you're looking at. And then it also has that Kelvin unit in there as well. So Kelvin's included in units of the entropy values. Okay, so let's move into Gibbs. Gibbs free energy is taking these two things that are governing reactions and putting them together so that we can see if that combination of heat and chaos is just right to make the reaction happen. And that's what it's describing for you here, since there are really 2 deciding factors for the occurrence of a chemical reaction: maximum entropy, so we want a lot of chaos, and minimum enthalpy, we want the least amount of heat, because heat is being released and exothermic. It says, how can you figure out if a reaction will really occur? Well, a scientist named Gibbs came up with an equation that takes both of these things into consideration, and we end up getting a value that sign will tell us whether that reaction is going to work or not. So there's a couple of things listed here, and I want you to highlight this part right here. Delta G is Gibbs. Yay! It's a letter that goes with what it actually means. So delta G being negative means that reaction is going to work. That combination of entropy and enthalpy is great. That reaction is going to happen. If it's positive, it's not going to work. And then we'll talk a little bit about this delta G being 0. Delta G at 0 is where there's this shifting point. Usually it represents a temperature where if we shift it just enough, we can make that reaction spontaneous. So delta G being 0 is right where we're at the point where, the reaction is borderline spontaneous or not spontaneous. So that's what that means by delta G being 0. Okay, so let's see how we use this equation. There's a couple of things we have to remember. Simple things, nothing crazy. We use this equation. This is our Gibbs free energy equation. Delta G represents Gibbs free energy. And remember, we're looking for that value to be negative to tell us the reaction's going to work. That is a spontaneous reaction. Here's a couple of things you have to remember, and it deals with the units of enthalpy and entropy. First of all, you have to make your temperature in Kelvin. So notice that temperature is part of our Gibbs equation. It's the change in heat minus the temperature times the change in entropy. The temperature being part of that equation, we have to put it in Kelvin because of the units of entropy. They have Kelvin in them, so we have to make that simple conversion. So remember, we just add 273 to go from Celsius to Kelvin. So we got to do that. The other thing you have to do is make sure that your units of heat match up. Delta H is usually in kilojoules per mole, and delta S is joules per mole. So we have to either change the joules or the kilojoules so that they match. So let's try example 8 together. Okay, it says, given the following information, determine whether a reaction is spontaneous at room temperature, which is 25 degrees Celsius. Now, first thing you really should do is look at your heat value and look at your entropy value. We know that being negative for heat, nature likes. It always favors that. So based on just the heat alone, this reaction should be spontaneous. Well, but we also know that nature likes a positive entropy. It likes chaos to be increasing. And this value for entropy is negative. So really I've got one favorable thing and one non-favorable thing. That's why I need Gibbs free energy equation to tell me, is this reaction going to work? Is there enough energy being released in combination with the temperature that it will compensate for that lowering in entropy? It will kind of offset that enough that the reaction can still work. That's where Gibbs free energy equation helps us out. Okay, so we're going to use Gibbs. Delta G is equal to the change in heat minus the change in temperature minus temperature times delta S. Okay, so let's see what we've got in our problem. We know the change in heat is negative 176 kilojoules per mole. Okay, I know that part. And I know that my temperature is 25 degrees. I need to add 273 to that so that my temperature is in Kelvin. So minus 298 times, that's Kelvin, times my change in entropy, which is negative 285 joules over moles times Kelvin. Okay, so I have everything put into my equation. I guess I really don't need that little bracket. But here's the problem. I got my temperature taken care of. I've got kilojoules and I've got joules. So I'm going to make a quick conversion, and this is the one I do so that it makes my number a little more manageable, not so big. I will change my joules to kilojoules by moving the decimal 3 places to the left. So 0.285 kilojoules. Now I've got kilojoules here and kilojoules here that are going to cancel out, or actually you're going to add them together. So they'll end up, you're keeping those. But we can add them because they're the same. Kelvin will cancel out. Okay, and then my moles are going to cancel out. So actually what you're left with is an energy value. Okay, and it should be kilojoules, sorry. Now it's just a matter of putting it into my calculator. So I'm going to multiply here and here first, and then I'm going to subtract. So I'm going to pause the video, give you a chance to put that in your calculator, and then we'll come back and take a look at it, see what you got. Okay, so once you put this in your calculator, you should end up getting an answer of negative 91.07 kilojoules. It asks if this reaction is spontaneous, and you just proved that it is because your delta G value ends up being 91, or sorry, your delta G value ends up being a negative number. Negative delta G values tell us that reaction is going to happen. Okay. Sig figs for this problem. Since we're adding and subtracting for our last step, we really should be rounding to the decimal place. And it looks like the decimal place that these go to, the least amount of places past the decimal is going to be that ones place. So really 91 kilojoules is what we would want to put for our final answer for that negative. It should be negative. Okay. So let's look at this very last thing that's on your notes. It's a table that tells us the combinations of things that work. And some of these will make sense, okay, definitely, because we know what nature favors. Remember that nature likes for heat to be negative and for entropy to be positive. So that combination is always spontaneous, no matter what the temperature is. Okay, it's always going to work. Now, on the flip side, nature does not want an endothermic reaction. That's not what it favors. And it also doesn't favor decreasing entropy. So this combination is a double whammy. Not ever going to happen. But the other two combinations are where we need Gibbs free energy to help us out, that Gibbs free energy equation. We have one positive thing that nature likes and one that it doesn't. Is the temperature the right place where we can get this reaction to really be favorable? And we can use our Gibbs free energy equation to figure that out. We can plug our values in, and if we get a negative value for Gibbs, then we know that reaction is going to work, that nature is going to let that one be spontaneous and happen. All right, and that concludes our video lecture on entropy and Gibbs free energy.